Okay, so now let's go for the choice of units in high energy physics. And you may ask why the name choice, right? So why I should go for a choice of units? I know lots of units, and after my master's, when I entered to high energy physics and do research in quark-gluon plasma, I know several units, right? So SI unit, your CGS unit, and CGS has also electromagnetic unit, electrostatic units. Then there is something called Heaviside-Lorenz unit. Okay, so many units I know. So then why a choice of unit has to be taught in high energy physics, and why I should be given with a choice? Okay, so many questions are there. So let me build up the story first. Okay, so we know I can write x square. X is essentially my 4x, right? So my 4 vector x. So this is equal to c square t square minus the 3 vector non-Newtonian space coordinate. Okay, so so this square. So p square, also the 4 momenta square, I can write m0 square c square, right? So this I know, and you can notice that c is coming always in all the equations. And another catchy point is, since these particles are subnucleonic, so these will be described essentially by quantum mechanics, and more often you may encounter the occurrence of H cross. So you may, wherever you find H cross, that is also a signature of quantum mechanics. Okay. So more often, the kind of equations we are going to deal with, you may encounter C, H cross, all these things. Okay. Can we have a choice to get rid of the C and H cross? So because H cross people can write in org, second inverse, or whatever units you use. Somebody may use joule. And when you go for velocity of light, somebody can write in meter, somebody can write in kilometer. So there are so many ambiguities. Okay. So if you look at de Broglie's relation between 4 momenta and wave vector of a particle, you will find E is equal to h cross omega. Okay. And 4 vector notation for momentum P will be h cross k. And I can write P as your time component, temporal component at E by C. And this is combining both. So then this P is the spatial component. And similarly, if you go to K, is omega by C and K. Okay. So the point is, without going to the details of these equations, the point I would like to bring to your notice is, in all of the equations or most of the equations, you may encounter occurrence of C and H cross. H cross is, as I told, the signature of quantum mechanics, or the subnucleonic domain of the universe, and C is coming from the relativistic factors. We are in the relativistic domain. So let's choose a system of unit for which H cross is equal to C is equal to 1. So both H cross and C, I am assuming 1, so that I can get rid of this occurrences which is coming repeatedly. Okay. And if someone wants to go back to the original unit of SI or CGS, so you can actually convert it back. Okay. So the algebra we are going to deal with, we will always take H cross is equal to C is equal to 1. And whenever there is a need of connecting back to our known language, so we can go back and do the conversion. Okay. So let's choose H cross is equal to C is equal to 1. And there is a rationale behind this. Okay. It is not that we want to get rid of these reductions only. There is a rationale behind it, and I will slowly migrate to that. Okay. So now the relativistic formula for energy, which was very complicated, right? So, I am so accustomed with not using C. Whenever there is a requirement of teaching to BTech students in IIT Indore, I always get confused with if C square is here or here, or C4 will come here or here. Okay. So this is essentially a choice, as I explained from the beginning, and our dimensional analysis can give the answer where C4 will be and where C square will be. Okay. It's not a big deal, but my point is, it is difficult. As you see, C power 4, C power 2, and where C will come, where H cross will come. These are, matter of ambiguities more often. And in the new system of a unit, when C is equal to 1, the equation is very simple. E square is equal to P square plus M0 square. And if I more often use my rest mass is M, not to be confused, of course, the convention matters. So it is just p square plus m square. So it is very easy. I don't need to remember it is c square or c4. Okay. So I guess some of you will agree with me that the new system of unit looks pretty beautiful. Okay. So in particle physics, the unit of energy is GeV. Okay. And as you are working in Alice let's see, so you know 1 GeV is 10 to the power 9 electron volt. And you know what is 1 electron volt, that also you know by now. And I am not going to discuss about that. And this is motivated by the fact that the rest mass of proton is around 1 GeV, because it is 938 MeV. So it is almost 1 GeV in the approximation. So this will give me a feeling. Okay. So if I compare any particle mass with respect to my known proton, this will give me a physical feeling. It is heavier than proton or it is lighter than proton. So this also motivates me that using the mass unit, if I say kg, gram, it is not giving me a feeling. You see, if I take 1 kilo of potato or tomato, so I have a feeling that, you know, if potato size is this, maybe 10 potatoes or 12 potatoes will make 1 kg, right? So if I just ask you the similar question, that how many protons will be there in 1 kg proton or 1 gram proton, definitely everybody will be confused. It's not that you cannot calculate, but you cannot get a physical feeling of it. Okay, so that is the reason, you know, comparing with proton mass gives me a physical feeling of the mass of the subatomic particles. Okay, so now once I am in the domain of C is equal to H cross C is equal to 1, this needs lots of conversions, as you know, and more often we encounter mass, momentum, and energy. So these three will go in the units of energy, which is GeV. Okay. And if you go to length and time, so they will be expressed in terms of GeV inverse. So slowly, once you go to these conversions and work it out, so you'll be accustomed with the new units. So in this new system of units, so if you do the calculation starting from taking the true value of h cross is equal to 1, or your 3 into 10 to the power 8 meter per second, which is speed of light in vacuum, so that is equal to 1. So you can calculate and show that these conversion factors are correct. Okay, more often you may need it, and usually people do a mistake in this calculation. So at least without just googling it and taking the number for your calculation, do it once in your life. Okay, so this is my suggestion to you. And for a counter check, as you can see, 197 MeV for me is equal to 1. Okay, so this is something you can actually remember. Okay, so 197 MeV for me is equal to 1. This I urge you that you should remember. This will help you in counter checking things. 197 can be approximated to 200. There is no problem. Okay, but and one more thing is 1 Fermi is equal to 3.33 into 10 to the power minus 23 second. This also you should remember. These two at least you should remember. Although we also know that 1 Fermi is equal to 10 to the power minus 15 meter, we remember by now. I don't ask you that remember other conversions, but these three, if you remember, that will help a lot. Okay. Why I'm saying you that you remember these, particularly these things. This conversion will go for a counter check, and if you remember 1 Fermi, more often actually we will be dealing with strong interaction, so the decay length or the QGP lifetime, and 10 to the power minus 23 second is our lifetime of strong interaction. So that is the reason roughly I can keep in my mind that 1 Fermi is the time scale or the length scale, because now we are in the natural unit. So for which actually the strong interaction holds. Okay. So because of these couple of reasons, I urge you that you remember these things. 1 Fermi is the length scale or time scale for the strong interaction. Perfectly all right. So the advantage of using natural unit in particle physics is we deal with strong interaction. As I told you, 10 to the power minus 23 second is almost the lifetime of strong interaction. And the decay length of particles can be expressed in terms of Fermi. So Fermi is the length scale. So we have a, if I say it is 3 into 10 to the power minus 23 second is the lifetime of something, you don't get a feeling. So the feeling is, it is 3 Fermi, okay? Or 4 Fermi. So 4 Fermi means the length scale also we know the particle is created and it can traverse this much distance before it decays. So that is also like the c tau, the path length of the particle. So this gives a physical feeling. This natural unit gives a physical feeling of dealing with strong interaction dynamics. And if you look at the energy scale is GeV and TeV, because taking the de Broglie equation, what I explained to you in my first class, if you calculate the energy requirement to probe the inner structure of proton, this is also taking you to GeV scale. So the scale also, matters in dealing with this or having a choice of natural unit. Fine. Is it very important that this choice of unit, and if somebody does a mistake and all that? I will convince you taking a practical example. How many of you know that there was a flight crash landing, I would say. So which is, if you Google it, it is a Gimli glider. So this airplane went out of fuel almost in mid-air, almost 41,000 feet. So how many of you know? I cannot actually see your hand raising and all that. So anyway, so few of you at least may be knowing this happened. And this happened because of a reason which you will laugh at, but nothing to laugh at. Okay. So because the reason is this Gimli glider going from Air Canada flight 143, going from Montreal to Edmonton, actually that ran out of fuel with 69 people on board. If you see, the pilot did a mistake of calculating the fuel and converting pound to kilogram. So essentially 22,300 pounds of fuel was filled instead of 22,300 kilograms. And people who have gone to United States, particularly Brookhaven or so, many of you might have gone. So in the Walmart or whatever supermarket you go, I was going to Walmart, you will find many things will be written in pound. And pound, roughly it is, I don't remember the exact number, roughly it is 400 something gram, okay, 1 pound. So, so it is, almost 1 pound is half a kilo kind of stuff. And if you see the amount of fuel the flight was carrying, it is almost half of what is required to travel from Montreal to Edmonton, right? And this conversion actually created so much of problem. But anyway, thanks to the pilot who was a glider pilot, and he could land it somewhere. So you can actually Google it to know the beautiful story of Gimli glider. So just Google Gimli glider and you will know more about particularly this thing. But my point is not Gimli glider. My point is this conversion of non-SI or CGS units to your natural unit will cost you sometime a lot. Okay, so this conversion matters, units matters. Okay, so that is why I warn you that in this domain of high energy physics, this while dealing with natural units and making a physical realization of the numbers, so you should be little cautious. That is my point of bringing this example. Okay, so system of units is a need or choice for the ease of the users at the time. I quote Max Planck here. I actually was going through this one very good book, thanks to Dushmantha for providing me necessary ebooks whenever I need it, because remotely now accessing many things, this virtual world, it is a bit different. So I quote Max Planck about the choice of units. So Max Planck says in one of his famous books on electromagnetism, the fact that when a definite physical quantity is measured in two different systems of units, it has not only different numerical values, but also different dimensions, has often been interpreted as an inconsistency that demands explanation and has given rise to the question of the real dimension of a physical quantity. Okay, if you ask about the real dimension of a physical quantity, there is no definite answer. Okay, after the above discussion, it is clear that this question has no more sense than inquiring into the real name of an object. So if I take one apple and ask you, what is this? So you will give the answer in English, it is apple, and then somebody will say in Odia, Seo, or something else, and it has no real name. It depends upon the language you are speaking. It is exactly in the similar fashion. The physical quantities expressed in different units or dimensions depends upon the choice of unit you are talking about. Okay, so there is no sacredness in this thing. So that is why you have to be very cautious. And quantities that are dimensionless in one system may have dimensions in other systems. So you have to be very careful here. Okay. And I just remind you, your famous book of J.D. Jackson on classical electrodynamics. If you look at the book preface, the second edition of the book was written in CGS unit, which is highly cumbersome. And in the third edition, the book is written, first part is SI unit, and second part of the book is in the same book, second part is in CGS unit. So this also, although it looks like crazy, but there is a justification written in the preface, you can have a look. And this also tells us that the choice of units is very important, and why second part is CGS and first part is SI. Once you read the book, you can understand. And if you look at a different kind of units, system of units written here, and you take the same quantity, sometimes it is dimensionless, sometimes it is having dimensions, and sometimes it is having complicated equations. Okay, and you may ask why I'm bringing these things. What is the rationale behind this for a discussion of natural unit in high energy physics? Point is, because we are accustomed with a particular language, once we migrate to another language, we'll face lots of problems. Okay, and you may say, what is the necessity of learning a new language? Exactly, while bringing up natural units for discussion, I could convince you that, okay, if you go to x cross is equal to c is equal to 1, so you have many things getting simpled out, and dealing with mathematics will be much easier. In fact, it goes with the rationale of proton mass around 1 GeV, 1 Fermi being the path length or the lifetime corresponds to the strong interaction lifetime of 10 to the minus 23 seconds and all that. Okay. So with this, I remind you also the SI unit, which we all are accustomed with. Whenever you feel free, you can convert it back and have a filling of the SI unit. Okay. So till now, as I told you, depending upon the necessity, people use units as and when required in different perspectives. I remind you imperial units. So in fact, I was not knowing about imperial units too much. Still, I took a Emirates flight to Geneva. So there actually, it was flashing on my screen that the pilot, the flight information says that the flight is going with this much speed, and that speed was actually in nautical miles. And I was converting to know, and I am again Googling it to know more about imperial units. And then I thought, why it is used? So if you look at one nautical mile, which usually this is the language of aviation industry, or the people, captain or pilots in sea and aircrafts. So they use nautical miles. So when I did little Googling and try to know more about the imperial units, so I was surprised to know that this approximately equals to 1 arc minute of a geodesic, which, this flight path is a geodesic. Okay. It is part of the great circle. Geodesic meaning is great circle. So it makes sense to them if they talk in the language of nautical miles, but for a passenger like me, it is nonsense to realize, even I was not knowing it is 1852 meters. Okay. So after Googling it, I came to know. It is not giving me a physical sense when I talk in a nautical mile language, but absolutely, if you go to the aviation language, 1 arc minute of a geodesic matters. Okay. So that is why, which domain of science you are talking about, that matters a lot. And for us, natural unit has a bigger sense. Similarly, in the same, flight also, I saw the speed of the aircraft is 0.89 Mach. So Mach I was knowing because, we know Mach is the speed of sound in the air, and depending upon that, you can say the aircraft is either subsonic or it is supersonic. Okay. So for your knowledge, this Mach number is used more frequently in fluid dynamics. Although we use hydrodynamics for understanding our Quark-Gluon plasma, but this Mach number is also more often used in fluid dynamics. Okay, so the rationale of my discussion here is the choice of units is a choice depending upon the need, and nothing very reservation about it, but you understand the rationale of using natural unit in high energy physics. Okay, so now with this, let me digress a little bit to 4 vectors, which I will be using as my language to deal with the kinematics of different decay problems. Okay, so let me introduce, is there any question till now before I go to 4 vectors? Looks like no, it was a good story, right? Okay, no problem. So let's go to 4 vectors. So the position time for vector x mu, I write mu is equal to 0, 1, 2, 3 as the indices, with x0 corresponds to the temporal component ct. Don't worry why I'm bringing up c now. I'll get rid of c, okay? Because I just now introduced natural unit. You may say, why are you bringing c? Okay, it is because I want to make a slow migration from your known knowledge or the units you are accustomed with to the natural unit. Slow transition is better. I don't want to make a fast transition. Okay, so because of that, my 0th component is ct, which is temporal component, and my x1 is x, y, x2 is y, and x3 is z, which is the spatial component. So now I can write I is something which is the temporal component square minus individual spatial component square, and using the Lorentz transformation equations which I discussed in my last class, you can show that this also equivalent to or equal to the coordinates squares in my S prime or the frame which was moving with some velocity, and both are inertial frames. So this I is called the 4-dimensional length element, which is Lorentz-invariant. Okay, so what quantity having the same value in all inertial frames is called Lorentz-invariant. This is exactly equivalent to r square is equal to x square plus y square z square being invariant under spatial rotation. So this is your 3-dimensional length element. R square is equal to x square y square z square. So now, I urge you to have little concentration, because this nomenclature or the kind of indices I am using, that will be quite useful in next classes. So if you are lost here, you'll be lost in the next classes. So be attentive a little bit. So I could be written in the form of a sum, okay, where the index mu runs from 0 to 3, and I can write this is as x mu mu. Okay, can I get rid of this summation? Because I don't like to write too much of mathematics and unnecessarily keeping in mind and making my brain CPU busy. So can I get rid of this summation? Okay, so let's go ahead. Let's introduce few more things. So to take care of the negative signs, let's first define the metric G mu. Keep in mind that I am following the convention of Griffith's particle physics now. Okay, because the metric can be dependent on the book. Okay, so to be in the same page, you try to follow, if you want to follow these things and you want to go back and study a little bit on this, follow Griffith's particle physics book. The metric I'm using, it is from that, so that we are in the same page. So you have noticed that the temporal component was positive, but the spatial component was negative. So to take into account that aspect, let me introduce G mu nu, okay, so that my G mu nu matrix or G matrix is temporal component 1 here, and all the spatial components are negative. There is a reason of doing like this, but in several other books also you will find my first temporal component is negative and other components are positive, because people have different arguments. Why to give positive to one and negative to so many people? Let's do the other way. Okay, In other books also you'll find these things. But nothing to worry. You can choose your convention, but better always to stay in the same page, same page. So the temporal component is positive and spatial component is negative, and it's a convention. Okay. So it is like, why x-axis is positive, right hand side of the x-axis is positive. No answer to this. It is a convention. Okay. So I can write my I as g mu nu x mu x mu. Just I replaced I just incorporated this negative sign taking care of. Okay. And this summation runs over all four components. So let's define a covariant for vector now. When I say covariant, it is mu, the Greek index, the index is down. Okay, it is covariant. When I go for contravariant, so my index will be up. So again, this is my convention. Okay, so then x mu, covariant mu, can be written as g mu nu x nu. So now you see, repeated index will be contracted out. So in that way, your mu, nu and nu, this will be contracted out at the end, giving you x mu. So that is the way to remember this. So the repetition will be contracted out in tensor language. So x index of mu is called contravariant for vector. And with the above definitions, so we can actually write my I as either you write x mu x nu or x mu x mu, so that up down doesn't matter to me. And as you know, when I convert one contravariant to covariant, my g mu nu will come up, and that will take care of the negative sign in the spatial component. Okay, so I repeat here that I can be written in this way, and to each contravariant for vector mu, a covariant vector could be assigned and vice versa. This I told you now. Okay, I can write a contravariant for vector like this with g mu up and a nu down. Okay, so this is contravariant, this is covariant. I can also make it reverse. And you should note that your elements in G inverse are actually same as G. So G mu nu is equal to G mu nu. So this is actually, you can show it mathematically. Fine. So given any four vector, let me say that A mu and B mu. So since this is equal, I told you earlier, and G mu is there when you make it contravariant to covariant. After you do the multiplication for vector product, you will find that component wise your temporal will be multiplied with temporal, like vector multiplication you have done it, right, in Newtonian algebra. So temporal will be multiplied with temporal, spatial will be multiplied with spatial component wise, and spatial components will carry all negative signs because of the metric I have chosen, where all spatial components are negative. And this four vector scalar product, so this is called four vector scalar product. This is Lorentz-invariant. And the best example is your four-dimensional length element. Okay. So this is called four vector scalar product. So people, from particle physics specialization in your MSc, you must be knowing all these things already. But anyway, this is a brush up for you. And since we are from many different universities and many different places, having the syllabi different in different places, it is worth introducing these things, okay? Because the aim of the school is to bring everybody to the same page, so that it is a good starting for all of us. Okay, so I remind you again, Einstein's summation convention, repeated Greek index should be summed up, okay? So that is the convention. So if there is a repetition like A dot B, so this is equivalent to A mu, A mu. So A mu, I do not need to write because any repeated is summed over. So then I can write just A dot B, and any A dot B four vector scalar product can be done in a way, A0 B0 minus A dot B dot. So this A dot B dot is essentially Newtonian vector product. Okay. So if I write then A square, so A square can be written as A dot A, which is A0 square, 0 component square minus A vector component square. The vector is your Newtonian vector. And this is temporal component, this is spatial component, right? So if you look at the mathematical structure here, so since there is a minus, it might happen that this square is higher than this one. So then ultimately your A square is greater than 0. So in this kind of events or this kind of situations, mu is called a time-like vector, time-like for vector. So what is the meaning of time-like for vector? The events in the forward light cone. So you see, this is a diagram, light cone diagram. Light cone diagram is little different to understand because your y-axis is time, x-axis is space. So all three components of space are encoded here. Okay. And events in the forward light cone. So this will correspond to events in the forward light cone here. And they appear later than origin. So these events will appear later than the origin, respecting the causality. Okay. And events in backward light cone, they appear earlier than 0. So essentially, 0 is the starting point. So anything backward will happen before, anything forward will happen after this. Okay. Only events in the backward light cone can influence 0. So this also respects the causality. And 0 or the origin can have influence only on the events in the forward light cone. Okay, these are just I have put for discussions. You may not need for your algebra you are going to do for vector or decay kinematics, but just keep in mind what kind of events are these. Similarly, in the similar situation, my S square could be negative. Okay, so this will correspond to space-like events. And the events are called space-like events, and there is no interaction with 0 because we are not talking about time here. And it might also happen that your temporal part is equivalent to spatial part. And in that case, your A mu is called light-like, A square is equal to 0. So this connects all those events with the origin, which can be reached by a signal of light. Okay. Light signal, because it has to travel with speed of light. Then the particle has to travel with speed of light. Okay, so in this situation, so this was just for completeness sake I showed you. So now let's migrate a little bit more to for velocity so that I can bring up energy momentum tensor and all that. Okay, so I have tried my best to make my migration very smooth without a big phase transition so that everybody is contained in the discussion. So the velocity of a particle in Newtonian dynamics, we have seen that v is equal to dx by dt. What is my dx? Dx is the distance traveled in the laboratory frame. And what is my dt? Dt is the time measured in the same frame. So Newtonian dynamics was like that. Okay, so I never talked about this frame versus that frame, right? So because everything was happening in my laboratory, Newtonian dynamics was very good to perceive, to understand. So my v was dx by dt, distance traveled by the time measured. Both are in the same reference frame, the laboratory frame. So let me make it a bit complicated by introducing proper velocity of the particle. And my proper velocity of the particle, let me write eta. Okay, don't get confused with slow rapidity here. Okay, so this is my eta, which is proper velocity. So this is dx by d tau. Okay, and d tau is the proper time. Although dx is the distance traveled in the laboratory frame, d tau is the proper time measured in the particle rest frame. Okay, that is why it is called proper velocity. But unfortunately, I could not introduce something like dx, something like proper x. Okay, because there is nothing like that. So you have to be very practical in the measurements. So in that way, after introduction of this, one can show that this mu can be written as gamma v. Okay, so this v, the Newtonian v, multiplied with the Lorentz boost factor will give me the proper velocity of the particle eta. So this you can mathematically show. Note that it is easy to work with proper velocity because only dx will get a Lorentz transformation, whereas d tau is invariant. Okay, that is not the case in my Newtonian velocity, where both dx and dt will get transformed under Lorentz transformation. So at least it is giving me a better handle when the new denominator is not changing or Lorentz invariant, whereas the numerator is only changing. So that is the reason possibly I will prefer to work with proper velocity compared with the Newtonian velocity. Okay, this is the justification. But at least one is helping me. So now from your 3-vector eta, let me migrate to the 4-vector concept. So now this eta mu is equal to d, I write x mu divided by d tau. And you can show that my zeroth component is nothing but dx0 by d tau, and x0 was nothing but ct, and I know how d tau is related to dt. It is dt by gamma, Lorentz boost factor. And at the end, I could show that my eta 0, the temporal component of proper velocity, is nothing but gamma c. I think I'm emerging in a beautiful way. Okay, the first component or the zeroth component is my eta c. Okay, if that is the case, now I can write my for velocity as gamma. Okay, remember I am writing in a contravariant way, so that is why minus signs are not here. If I will write in a covariant way, so I have to introduce here minus signs for the special components, or I should take care of my metric in my algebra. Okay, so I can write component wise for velocity as gamma c vx vy vz. So this is called proper for velocity. So as per our convention, special components bring up negative sign for covariant current tensors only. And you can see I have written in a contravariant way. So that is why I have not done a mistake. So we can show, as I told you, that scalar product of 4 vectors would be Lorentz-invariant. So now, can you do this algebra taking eta mu, do the 4 vector scalar product, you should get c square, taking these components. Okay, so do that once at least. Okay, because unfortunately we cannot go to the board because of the virtual teaching. So I urge you that you do it and have a realization of few things what I am writing that we can show. Okay, so then in principle my c square should be invariant. I know that it is invariant, and then my scalar product of the 4 vector is Lorentz invariant, so I'm fine. I'm in the same page. So which is Lorentz invariant, and also proves that 4 vector scalar product is Lorentz invariant. Wonderful. So with this, is there any question? Because it was a new concept of bringing 4 vectors. Is there a question on this? Looks like no, or very simple, or I am going fast, or it is not understandable. I do not know what I am doing. Right? That is the difference between a virtual photon and a real photon. Okay, let me again make the assumption and develop my theory. So I assume that everybody is content. Nobody is lost. That is what my assumption is. Okay. So now let me bring up energy momentum per vector. So if you have to start from the scratch, which way you are going to define momentum? Momentum is simply mass into velocity. Fine. Velocity could be ordinary velocity and proper velocity. This I discussed. And classically both could be shown to be same. Okay. In the Newtonian reduction, okay, non-relativistic reduction, both could be shown to be same. Perfect. So in the relativity, momentum is the product of mass and proper velocity. So that is what I showed you. Okay. So now my free vector P could be written as M 3 vector eta. So if I migrate to the 4 vector, so this is my P mu is equal to M eta mu. So now there is nothing called ordinary mass or proper mass, right? It is mass. So that is the reason there is no distinction between that, but velocity has ordinary velocity and proper velocity. So now P mu could be written as P M eta mu. So the special component of mu constitutes the relativistic momentum vector. Okay. So now P vector is my gamma mv. Okay. And gamma I know 1 over 1 minus b square by c square. So then my the ordinary momentum or the Newtonian momentum is essentially your P is equal to gamma mv, which is so this is relativistic, but the special component, instead of saying special component, I told Newtonian, sorry. So it is a relativistic part of the momentum. And the zeroth component of the 4 vector momentum is gamma mc. Okay. So now the relativistic energy could be written as gamma mc square, which I know from Einstein. So this can be written as mc square divided by this Lorentz multiplied by the Lorentz factor, which will, if you do little bit cross algebra, you will find that my P0, the zeroth component of the for momentum, P is E by C. Okay. So if that is E by C and third component is known, so I can now write the energy momentum for vector where my P mu is equal to E over C. Again, this is contravariant. Okay. And this Px, Py, Pz. And these are not carrying negative sign, not to be confused because I am talking about contravariant for vector. If somebody writes P mu downstairs here as a subscript, then it will be E over C minus Px minus Py minus Pz component wise. Perfect. So one can actually show taking this, okay, and when you do this algebra for vector algebra P mu, essentially exactly in a similar way you are going to do. How are you going to write it? Can anybody tell me how I am getting m square? Yeah, somebody should speak up. So I have the input P mu is written in this way, and I am demanding that one can show that P mu is m square. And in principle, scalar product of the four vectors should be Lorentz-invariant, and on the right hand side you get m square, and m is invariant mass at the end.
Sir, from the energy momentum relationship.
Bhagirathi.
Yes, sir.
Okay. So how will you proceed to show that P mu is m square?
Sir, the contravariant P mu is this, and the covariant P mu will be minus of Py minus Pz. If you multiply, then it will give E square minus P square,
which is relativistic energy.
So next step, it may not be clear to everyone. So what you are saying is in the covariant one, these things will be negative. So then you make a multiplication, right?
Yes, sir.
So how do you do the multiplication? So the answer is the way you did in the vector algebra, right? Component wise, it has to be multiplied.
Yes, sir.
So when you do that, so your next step will be E square, okay, plus P square. Sorry, minus P square. Right. And then your energy, relativistic energy formula is E square is equal to P square plus M square.
Yes, sir.
Absolutely correct. Okay. So then you get your M square at the end. And I also verify that, okay, this is Lorentz-invariant. Everybody, it is clear to everyone or no? Because why I'm saying is, in all kind of kinematical problems, I would urge you that you use for vector, not your conventional way of momentum conservation demand and demanding energy conservation. That will be a big algebra, 2 pages. 2 pages versus 1 paragraph, it is your choice. So I would say that you use for momentum. Okay, so that is the reason I am demanding that you should go for momentum, so that your algebra is easier compared to your known way of Newtonian stuff, demanding momentum conservation and energy conservation separately. Anybody has any problem with up to this? Hopefully no, or maybe you are knowing already. Anyway, so let's go ahead. So this is coming because your E square is equal to P square plus M square in natural units. So I'm not going to repeat that I am in natural unit, I am in natural unit always. Okay, wherever you do not find C, so it is perfectly all right, I am in natural unit. Okay, and in my convention, your P with an arrow is your classical momentum, Newtonian momentum. Okay, if I do not have arrow, it is for momentum. Okay, sometimes I may write mu, I may not write mu also. Okay, because that Einstein's convention I can also apply. Okay, so as I discussed earlier, your P square is equal to M square I'm getting from here. This could be greater than 0 also. Okay, so because you can write in the temporal square minus spatial square. So this is the case where your temporal square is higher than the special square. Okay, so this corresponds to ordinary or massive particles with mass greater than 0, and it might happen that p square is equal to m square. It's always true, but this is equal to 0. So then this corresponds to massless particles like photons, gravitons, etc. And mathematically, it could happen that p square is less than 0. Okay, that will correspond to virtual particles or particles with negative mass, which was conjectured by E.C.G. Sudarshan. If you Google it a little more, the Indian famous particle physicist who did good contribution to particle physics is E.C.G. Sudarshan, and he conjectured this particle tachyon, which is not yet discovered. Okay, so this is a particle of negative mass. So more interested people can look into that, but it is coming from one of the mathematical possibilities that p square could be less than 0. Okay, that corresponds to tachyons or virtual particles. And this could also be 0, p mu could be 0, that's for vacuum. So more discussion you can actually have a look at in textbook. Okay, so now note that the relativistic equations which I wrote, that p is equal to gamma mv or E is equal to gamma m, they do not hold good for massless particles. Okay, what is the solution then? Because I say that photon is massless and I say that it has a finite energy, it has finite momentum, right? But mathematical formula says that once I put m is equal to 0, momentum has to be 0 and energy has to be 0. So what is the solution? The solution is, when mass is equal to 0, it is only allowed if the particle travels with the speed of light. Okay, so these relativistic equations, they do not hold good for massless particle, and as a solution to this, m is equal to 0 is only allowed if the particle travels with speed of light. There is a beautiful discussion on this in Griffith's particle physics book. Okay, so have a look at that. And again, I urge you that you have a look at Griffith's particle physics book on this pion decay problem to mu1 plus antineutrino, and you will find that the normal way of conserving energy and momentum versus the four momentum method, which one is elegant. So you can have a look. If you do by yourself, it is good. If you find or fumble with that, you can actually have a look at the solution given in Griffiths. At least once you should have a feeling of this. One more problem is also given in that book, that you calculate in Bevatron, when first anti-proton was created, it was essentially one proton at rest, another proton, it's like a fixed target experiment. So another energetic proton was brought in and collided with the P. In the final state, what could happen is P plus P, then P plus P bar. Okay, so the question is, what is the threshold energy of the reaction? Use 4-vector method. So I have a dedicated discussion in the next class on how to calculate threshold energy, because that is very much important for all of us. So how you employ this 4-vector method to calculate threshold energy. So I will give you a recipe. So if you follow the recipe, you can calculate anything using 4-vector. Okay, so you don't have to worry at all. So next class, be tuned. I'll discuss about that. But one more thing I would like to bring here is, can anybody tell me the production of antibaryons, particularly antiproton, needs more threshold energy? Can somebody justify me? Anybody to speak up? And that is one of the reasons, even if I wanted to create an antiproton in Bevelak, the energy required for the proton, incoming projectile proton, was 6 GeV, whereas antiproton mass is 1 GeV around, right? So why higher energy is required for the production of antibaryons?
Because sir, antibaryons can only be produced.
No, wait. Who is this Nilkamal?
Yes, sir.
No, don't answer. I know you know the answer. Somebody else.
Sir, I think as
Rakesh.
per the baryon conservation, yes, sir.
Yeah,
For
go ahead.
baryon conservation, For baryon conservation, antiproton cannot be produced lonely, so there should be a proton production for that. So that's why
But
there
what is the reason? What is the reason? You are close to the answer, but what is the reason? Be
for the
exact.
conservation of baryon number.
Correct. So when you are creating antibaryon, essentially, initially you are taking two baryons per collision, right? In the final state, you are creating your antibaryon. So you have to conserve the baryon number. So along with P bar, you have to produce another P, right? So that is the reason if you look at the final state, although PP was produced and PP bar is the associated production is also there. Although associated production is reserved for strainless production, don't get confused with my wording. So P bar has to come with another P or N. Okay, if allowed, N can also come, neutron, right? Because I have to conserve baryon number. I don't care who is coming. If my baryon number is conserved, I am fine. So that is why Feynman told, anything allowed by conservation numbers can happen in the laboratory. Nobody can stop it. Fine. So this justifies that, when you produce antibaryons in the laboratory, your threshold energy has to be higher. And to your surprise, the energy when that exceeded this threshold energy of 6 GeV, in Griffiths, you'll find the total energy required, the threshold energy is 7 GeV, because this participant, the stationary proton is also there. Okay, that goes to the calculation of threshold energy. So threshold energy for this reaction was 7 GeV. And when this projectile proton just crossed 6 GeV, so people started seeing this antibaryon production, and it was 1952 Nobel Prize. Okay, in Bevelek. So you need 6 GeV proton. That time when GeV-TeV was not introduced, it was called BeV. And BeV, you should know a little bit of history. That will be very exciting for you. So it was earlier called as BeV, because BeV is named after Bevatron. And Bevatron was in California Radiation Laboratory, Berkeley. So now it is called a Lawrence Berkeley Laboratory. So that time in 1952, it was called as California Radiation Laboratory. Okay. So if you look at, just I have put out of excitement this one. So 1952-54 when it was operating, so this Bevatron looks like this. So you Google it and know a little more. And compared to this, when you look at 2010 Large Hadron Collider, where you people are working now, okay, you'll find it is more beautiful, not because it is black and white picture versus color picture. So it is beautiful in my language because lots of technological advancements have happened, starting from electrical engineering to cryogenics, vacuum technologies, and many things. So whatever was required to be assembled in one room, now that can be assembled in a small table. So that is the reason, we could go up to, very big accelerator and bigger energies. Okay, this is just to excite you. And now don't get worried because, seeing LHC accelerator is a matter of chance. For example, first I saw in 2003, then almost after 17 years or so, so this year I could see it. So it's a matter of chance. When you are at CERN and you are allowed to go inside, there is no beam, then only you can see your accelerator. Okay, not accelerator, you can see your Alice setup. Okay, and accelerator seeing will be again another fortune. So don't worry, high energy physics, always you cannot see your detectors, accelerators, nothing to worry, one day will come. Okay, this was then, and it is